Well, good morning, good afternoon, and good evening from Helsinki, and welcome to the Pulse of Networks webinar series, episode 15. My name is Claus, and I'm the CTO of Creanord. Today's topic is advanced TWAMP monitoring techniques for 5G networks. But before we start, I want to tell those of you that might have missed one or two of the previous episodes in this series, do not worry. So all of these webinar episodes are available on our website as well. If you go to our website, you can check under News and Insights, and you'll find a selection on-demand webinar. And from there, you will find all the previous episodes as well, if you are interested. All right, but let's get started. So before we go into the nitty-bitty details, let's have a look at a little bit on the background of TWAMP monitoring. So why do you actually need active monitoring at all? Why not resort to traditional methods like SNMP polling or just traditional fault management to manage the performance of your network? And the very specific reason why you need active monitoring is actually just one word, and that's video. So today, video drives all data on any transport network there today where you have customers connected. Streaming video, social media videos, and so forth. In Ericsson's mobility report from June this year, they note that mobile data has almost doubled in 2 years. And video is estimated to account for 71% of all mobile data out there today in the networks. And according to the report, it's estimated to reach 80% in 5 years. This varies from country to country, of course. In Finland, for instance, this percentage of video is even higher. Operators are citing very staggering figures close to 95% or 97%. So video is the majority of all the traffic, really. And video is challenging because it causes a lot of burstiness on the networks. I will explain why later in this presentation. So, as the video traffic increases in your networks, you need to find a way to cope with this growth. Another interesting fact from the Ericsson Mobility Report is that the top 10% of data consumers actually use 70% of all the traffic on the network. On the other hand, if we look at the light consumers, those with data consumption below 5 gigabytes per month, but still accounting for 2/3 of the entire customer base, a significant portion of that traffic is communication services with strict quality requirements such as voice, video conferencing, video calls, and so on. Now, so why is this important? Well, if you think about it, 10% of your end customers or users are actually degrading or in the risk of degrading the user experience of 2/3 of your customer base. So a large portion of your customer base is perhaps not looking for the greatest download speeds, but rather looking for a very good overall user experience when using the networks. We all know how annoying it is if your team session or voice call is not working or when the quality is degraded. So this is something that you want to focus on to keep your network quality and user experience in a very good shape if you want to hold on to 2/3 of your customer base. And certainly the rest are equally looking, of course, for a very good experience of the network. And this fact is also supported by another study done by McKinsey in 2022. And in this study, they looked at 3 factors: why end customers choose a specific service provider, why they left that provider, and what drives the customer net promoter scores. And in all of these cases, roughly 40% for each of these 3 cases, by far the largest category in all these three cases was related to network. So if you think about it, the fundamentals of your business is to attract new customers, make sure that the customers you manage to obtain are not leaving you, and then that your customers are spreading the good word around to other potential new customers. And in all of these 3 cases, the most important factor to manage is to ensure that your customer has a good network experience. So so you can also note from this this study here that price is, of course, very important, but it's not the driving factor. It is the network that is the most important thing to focus on. All right, so why is the video then destroying the performance of the networks? And to understand this, we have to look at how streaming video works. And in a previous webinar from this year on how to build outperforming networks, we touch a little bit deeper on this topic. And I just want to reiterate the main points here in this webinar. So streaming video is distributed in small, typically 4 to 10 second long video segments. And the video player will hold a small buffer of video segments and will load the new segments whenever it completed playing one of the segments from the buffer. So this means that every 4 to 10 seconds, the player will download a chunk of video using TCP as a normal TCP web file download. And the issue lies in that the TCP in its nature tries to consume all the bandwidth that is available. And that is the root cause of the performance issues and why video is so challenging to manage. Depending on what the download speeds you have, there will be microbursts as the TCP session downloads the videos. And to look at how this looks in reality, I have on this graph illustrated 2 real-world scenarios where I am actually myself watching the first episode of House of Dragons. Now, in the above graph, I am in my home watching it, and there we have a 30 megabits per second download link. And in the second graph, I'm looking at the same episode from the office, where we have a faster 200 megabit download link. And we can clearly see this microburst in both of the graphs. But if you look at the microbursts in my home, they are wider. They take a little bit longer, perhaps 400 to 500 milliseconds. Whereas in the office, these bursts are much shorter, perhaps 100 to 200 milliseconds. And the spike is much higher, of course, because I have a much higher bandwidth, and the TCP session will try to download that segment as fast as possible. Okay, so fine. So what? You have a nice download speed at the office. What does this mean for the transport network? Well, the interesting part here is not the download link for one of the users and how that behaves. The interesting part comes when we start to look at what happens with aggregate flows. How does that look in the transport network? And that's what we are looking at the next slide. So here, what I have done here is basically simulated a lot of users all watching House of Dragons. And in the first graph, I have users watching House of Dragons with a 30 megabit per second download link. And in the second graph, all of the users watching House of Dragons has a 200 megabit download link. And every user, of course, starts at random times to watch it. So that's been taken into account. And if we look at the burst patterns here, it's quite interesting. So already, if we look at those with the 30 megabit download link, we can see that already this traffic is quite bursty, because when we aggregate it, all of these spikes get aggregated together and they don't match in perfectly in time. So there will be certain spikes, there will be certain bursts. And as we can see, we have so much users that we have an average of 400 megabits per second traffic on the link. But the bursts can go up to 65% above that average, up to something like 650 megabits per second. So it's a significant burst, or even on that link. But the interesting part is when we look at the second graph. So there, the users have much faster download links, the bursts are more aggressive, and when we aggregate them together, we actually get very aggressive bursts that can go even 200% above the average utilization for that link. So in the second graph, if we have a 1 gig transport link in our transport network, we would already be at certain times for a short period of time exceeding that transport link capacity. Now, when we exceed the capacity of the transport links, the packets get buffered into network devices, they get delayed, and if you get a lot of packets that get buffered, some of them will even get lost, will be dropped, and so the packets are lost. And that means that your maybe not your video service is not necessarily the first to see this degradation, but it's actually the voice services, all those that from the previous slide, those 63% of the users that are actually starting to get affected by these degradations. So this is, of course, generally a very important fact for any data networks out there today. We are particularly talking today about 5G networks because that's a specific issue. Once you have upgraded from 4G to 5G, you're actually now offering your end users possibilities of perhaps even reaching 1 gigabits download speed. So when they start consuming video, you are going to see more and more, you're going to be moving kind of more and more from the upper graph to the lower with more and more bursts, very aggressive bursts. And that is what is degrading the quality in your network. Okay, so far, let's summarize what we kind of introduced here. So if we look at how you should then cope with this situation, how should you monitor your quality in the 5G networks? Well, some of the operators have so far related on traditional methods like SNMP monitoring, where we're using the SNMP protocol to go out, pull data from the devices, and then look at perhaps 5-minute averages, or if you are an advanced user, maybe a 1-minute average for the link. But if you look at from the previous slide on those bursts, they are much shorter. So a 1-minute average for the link I illustrated will just show that you have a 400 megabit utilization, and you don't actually know whether you have the graph above with 60% bursts or the graph below with 200% bursts. You have no way of knowing from that data. And it's really 1-minute averages is already typically stressing devices. It's not really feasible, or even for some devices, even technically possible to go below 1 minute to increase the polling times. a second option. So this is not an option, but a second option you might consider is passive monitoring. It's a good option for many use cases. But when we are talking about monitoring the health of transport networks, it unfortunately falls short, because passive monitoring solutions are quite expensive, and you typically deploy them centrally, and you have the visibility of the central big pipes in your network, but you really don't have the visibility out to the transport links further out in the network. So you don't really know how those bursts look at your transport links close to the end users. So that is the reason for the topic today, and why you need active monitoring. You can still, with the active monitoring, you can still locate the probe centrally, but they are still providing an end-to-end view out over all of the network. And in fact, you can also, even though you have it centrally located, you can also have a segmented view of link performance as well. Let's look at this a little bit more in detail for active monitoring, and how you should build your active TWAMP performance monitoring solution. The key fact here is that you centrally locate the probe, typically at an EPC site, but it can be some other core site in the network. And this probe will send out TWAMP packets to the base stations and any of the intermediate routers in the network. And the key fact here is that these routers and base stations have a TWAMP reflector embedded. Nowadays, all of the major vendors support the TWAMP protocol, so they have this functionality embedded in the devices. And this makes this modern type of building TWAMP performance has many benefits. And the reason I want to point out this type of architecture is that in some cases you might deploy TWAMP monitoring, but you are perhaps using the TWAMP monitoring solution from one of the EMS vendors, and it's a good solution for parts of the problems, but it doesn't cover all of the issues. With the central monitoring approach, you get a full view of all of your vendors in the network. So it's a true multi-vendor view, because we are using the standard TWAMP protocol, but we are using a central probe. So we have all the data in one system. It's of course very cost efficient. You only need to install a few physical probes, and when we are talking about 5G, it can also be, of course, a virtual probe. Which you are running at the EPC site as a cloud native function, and so it's very cost efficient. Your data is also consistent, so the same system is collecting all of the data, consolidating it, aggregating it, analyzing it, and reporting. So regardless of the vendors, you are getting consistent performance data. And of course, it's fast to deploy as well. You only need to install maybe a few physical probes, or even just deploy the CNF at the EPC sites or your data centers. And then you need to just enable the TWAMP reflector functionality in all of your devices in the network, which you can then do remotely. So there's no need for additional site visits all over the network. You just need to deploy the probe and then enable the TWAMP reflection. So it's very fast as well. So here we talked a bit generally about TWAMP monitoring, and then in this there are, of course, very many basic, nice things you can do with TWAMP to just monitor basically the delays, delay variations, jitters, report on that, and use that to monitor your network. But in today's session, wanted to show that there are also additional techniques that you can use with the TWAMP monitoring to solve very, very difficult issues in the network. And we have a few scenarios that I want to dive into today. Let's look at those next. So a few cases on verifying the QoS and configurations and your hardware in the network. Again, as noted, where as you move to 5G, you will introduce more service classes. There will be more configurations have been done in the network, and you have more services on your network with strict quality requirements and divided onto multiple service classes. So you need to verify that these quality of service configurations are correct. And TWAMP is actually a very nice way to verify all of these configurations and ensure it in an end-to-end manner. As we are monitoring the whole network, the whole data transport network with TWAMP, you can use the measured profiles to verify that your quality of service configurations are correct and that your differentiated services are actually getting the treatment that they are expecting. So in this graph, I illustrate again a real-world situation from one of the networks we are managing, where you can see a graph in the above graph, we have the best effort traffic being monitored, and in the below graph, we have the real-time traffic being monitored, and to the same base station and at the same times. And when you look at those traffic patterns, you can clearly see both in terms of the delays and how that varies over time, and the jitters, that the best effort and real-time profiles are very similar. Actually, also the orange small spikes there are the packet losses, and they are also very, very similar. And this clearly shows that there is something wrong with the QoS configurations. We should see a much better profile for the real-time traffic than the best effort. So this is a very easy and nice way to verify the configurations, and you can also then troubleshoot where in the network those misconfigurations are, so that you can find the root cause. If you are monitoring all the intermediate devices as well with the TWAMP, you can just look at the similar traffic profiles for the intermediate routers and devices, and see if the issue exists for the intermediate ones, and find that intermediate device which is the first one in the path, to show this kind of incorrect profiles. And in that way, you can find which device that is most probably misconfigured, and you can then fix that issue. So it reduces the troubleshooting time tremendously. Another way to also verify both, in some way verify the QoS configurations, as well as identifying probable congestion situations in the network end-to-end, is to monitor the differentiated services code points and if they change. So each of the TWAMP packets sent out will have a specific service class marked in the packet, and then the probe will monitor the returning packets back and see if this service class has changed. And depending on what change has happened, you can then determine a probable cause of that change. So if you are using the assured forwarding service class and you have used the gold priority sending out the packet, and it comes back as silver or bronze, it is very likely that somewhere along the path you have a congestion situation. So you probably need to look further into that and upgrade the capacity of your network, or do some reconfiguration, re-engineering of the traffic paths. And if the return packet has a totally different service class, typically it might come back as a best effort class, although it was sent out with a higher priority. So that's then an indication that you probably have a QoS configuration error, excuse me, somewhere in the network. Next scenario is also about finding quite tricky network issues, and that is by monitoring using different packet sizes when you are sending out the TWAMP packets. So typically, when you are monitoring using TWAMP, the packets sent out are quite small, but there can be some specific difficult situations. For instance, if MTU values are set wrong, or you have some specific hardware issues, that the small packets actually get through, but if it's a bigger sized packet, those packets get dropped. So to find this kind of more difficult performance issues, it's good to configure a measurement where the probe is actually sending out several different sized packets. So for one measurement interval, the probe will send out a small packet size, and in the next measurement interval, it will alter that packet size, send up perhaps a medium-sized packet, and then in the next measurement point, it will measure using a large packet size. And that means that you are measuring the performance that your users are getting for the different packet sizes, and you can catch issues that you are not catching if you are just using the small packets. So this is a very nice way to catch situations which you would typically spend a lot of time to identify the issue. A little bit of a similar situation is when we are having link aggregation situations, or we are using equal cost multipaths in the network. So in a traditional monitoring scenario, when you are sending out the TWAMP packets, all of the packets will follow the same route in the network, or they will traverse through the same link aggregation member, typically. So you are not actually testing all of the paths or all of the link aggregation members. However, it's possible for the probe to create entropy in the test packet, so that there are actually multiple flows being sent out and being hashed differently, so that if you have enough entropy, you will actually test all of the link aggregation group members and all of the equal cost multipaths. And thus you are getting visibility into the full network again. So if it's a link aggregation member that has some hardware issue, it's dropping occasionally some packets or something similar, you will catch those issues that you might not have catched if you hadn't used this feature. So these are multiple scenarios now which are very, very nice to find difficult network issues. Now, next, I'm going to go into another, sorry, I pushed the wrong direction. So next, I'm going to go into the next level of monitoring. So we talked about the basic monitoring features and how you can use that to catch the difficult network issues and so forth. Next, there's also a very nice way to measure the user experience using the data from TWAMP. So again, from the beginning of the presentation, if you remember, that 10% of the high data users are destroying for 63% of the users the network performance. And these users typically use a lot of voice services, interactive services, video calls, and so forth, which are very sensitive to delays, jitters, and packet losses. But if you are monitoring these basic KPIs, like you are looking at the specific jitter, you are looking at some perhaps a little bit of packet loss, you still don't really understand what type of experience the user has. So what if there was one packet lost and there was a certain jitter? How did that actually affect the user? Now, there are very advanced formulas, thanks to the ITU, which can take the KPIs that you measured by TWAMP and calculate a mean opinion score, which has been used for a long time for voice services. And it's a very nice measure because it takes all of these KPIs, and it's also taking into account the type of codec that you are using and what sort of jitter buffers you have. So of course the used codec will also have a big effect on the actual user experience. And then it takes all of these factors into account and will output a value from 1 to 5. And the nice thing is that it takes all these factors into account, and then you can see on a very simple scale, basically, that if you are, when we are talking about mobile networks, it's very difficult to get up to the very satisfied level, because even the codecs will do fairly advanced compression down to very low speeds, which already affects the user experience. But you can easily get above 4, which is still satisfied users. And then you know that if your MOS score is between 3.6 and 4, then you are already starting to get, some of the users are starting to get dissatisfied with your voice services or running voice services over your network. And then when you get below that, it starts to be critical. So many get dissatisfied after below the 3.6 level. So that's a very nice addition to get an overall picture of how your network looks like. What type of user experience in terms of voice am I offering? And the voice is very important for many of your users, as we looked in the beginning of the presentation. And I have a final scenario to look at, but it's not the least of the scenarios. It's the most important, actually, because this is where you want to go. So so far we have looked at how I should monitor my network and react to issues, and that's all fine, because that's the first thing. We need to get very agile and be able to react very quickly to when there are issues in the network. And that's where we need to improve first. But the ultimate goal, of course, and what we are targeting here at Creanord as well, is that you need to get proactive to how you manage your network. You need to actually be able to identify potential issues before they are affecting the end users, and that's what I'm talking a bit about in this last scenario. And again, and this links back to the video again that we started with, because we have a lot of these microbursts And I have two scenarios. So actually, again, these are from real networks. This is real traffic, real measurements that we have done. And this is from one network where we identified two types of sites. So site A is a site that is kind of on the verge of becoming congested. But if you are looking for site A on the average delay, it looks very good. So if you are just monitoring the average delays, you're not even gonna be worried when you are looking at these graphs. It's 3 milliseconds delays. There are some very occasional jumps, perhaps 0.5 millisecond or so. Nothing to be worried about really. But the thing here is that if you are also looking at the maximum delays, you will be able to identify these microbursts and start to see when they are actually starting to affect customers. So in case of this site A, when you look at or on the right side, we look at the maximum delays. And then we start to see that actually the situation is not quite as good as it looked when we looked at the averages. So the maximum delays can go up to above 15 milliseconds there in the graph occasionally, which is perhaps not yet catastrophic, but it is a warning indicator. And that's the point here. You get warning indicators that you are starting to meet the limits of your links. If you remember from the earlier slides, if you're using SNMP to collect the utilization data from the traffic, it's just going to say that, you know, it's a 40% utilization. You have no issues. And then you, as we saw from those slides, it depends a bit on what kind of users you have, how high speeds they have on their download links and so forth. So that 40% utilization doesn't really tell if you have an issue or not. But this maximum delay is actually telling you whether you have an issue or you will start to have an issue in some time in the future, because here we can see there are some microbursts. We can see from the patterns, it's something we see in many of the networks. It's around evening time and towards the midnight when people like to watch video particularly much. But still perhaps not alerting, but something to take notice of. Now in site B, we have another situation where we can actually see that we are already in the red, so to speak. Now, again, if we look at the average jitters for site B, there's still nothing to really be alarmed of. We see the same nice basic average delay that we saw for site A, or something like 3 milliseconds. Occasionally, my delay will go up to 8 milliseconds. So why should I actually worry? Well, if you look at the maximum delays, you can see that there is some occasional spike there, actually reaching even 150 milliseconds, which is totally critical for many of the voice services. Your jitter buffers will get empty and you will get cracks in voice or maybe lose the whole connection. But we see even more microbursts reaching perhaps 50 milliseconds, which is still a very critical level for your delays. You should be worried for these types of sites. So here you can see that with a solution where you can look at both the average delays and then investigate also the maximum delays, you are able to be actually proactive on how you manage your network. And it's a very nice tool also in the sense that you can determine where to focus your investments. Don't put more capacity where you don't need it. Put it where you actually do need to upgrade, where it's gonna affect that jitter. So the maximum jitter, that's still not affecting all of the users, but we know from the maximum jitter that if it means that some of your users are already getting a bad user experience. And if you want to avoid that, then you should add more capacity, re-engineer your network, do all of that traffic engineering stuff to get those jitters down, so your user has a good experience of the network. So let's conclude this session. Video challenges the user experience for majority of the users in the 5G networks. I hope my slides in the beginning of the presentation kind of hinted a little bit why this is, and why this is something to truly be worried about and take action. I hope I also show that the traditional performance management approaches that many use are no longer viable in these 5G networks dominated by video. We are reaching 80% globally in a few years. Many countries are above 90%, and the trend continues. Fortunately, there are things you can do. You can deploy a centralized active monitoring solution with TWAMP, which provides you the multi-vendor view of your whole network, and that gets you in control of your delay variations, packet losses, but there are actually also a lot of other network issues that you can actually fix with the help of TWAMP, which I talked a little bit about today. And the ultimate goal, which you can also use TWAMP to achieve, is of course to be proactive and identify the bottlenecks early in the process. Put your money where it matters the most and affects the user experience the most, because as the study shows, your network is the major factor why you will get new customers and why you might lose your existing customers. So take care of the network. Just briefly about the Creanord Pulsar solution. So it's a full performance management solution, including also SLA reporting for managing not only mobile networks, but all sorts of data networks. It has very good monitoring capabilities, including TWAMP that we talked about today, but also many other protocols. It has a full suite of also service activation testing, so you can also verify before going live that everything is okay. You have SLA reporting, so you can prove to your customers that you are delivering what you are promising, and you can integrate it with all of your other OSS solutions, so you can utilize the data. It's not a separated data lake, but you can integrate that data into all of your other tools in your OSS stack. And we have a full range of probes, both for physical and virtually testing the performance. All right, so that's all I had time for today. If you have any questions, you can put it in the chat, but or if you want to prefer to talk to me directly, you see my email at the bottom of the slide. Check out our website. We have, as mentioned, we have all the previous webinars there. We have information about our solutions, and if you want to set up the online demonstration or do a proof of concept in your network to check how your network is doing, just contact me and let's look at how your network is doing today and coping with the video of today. So thanks everybody, and hope to see you in our next webinar. Thank you.